This is Mr. Lee's physics class. I'm Mr. Lee. Starting from this video, we'll focus our discussions on gases. But before we can actually dive into it, there is one important physical quantity to learn, the pressure. Have you ever wondered why a stab and a punch, even if with the same force, would cause different damages? And I suppose you know very well that a stab hurts much more. It turns out that it's because of the different surface areas. A stab by a sharp knife, when compared to a punch of the same force, has its force exerted over a much smaller surface area than a punch. That's because a knife has a pointed tip where the force acts, and its area is very small. But for a punch, the surface on which the force acts is over the entire fist, and is a much larger surface area. It's kind of like the force is more concentrated on a small tip in the case of a knife, which makes it hurt more. And pressure is the physical quantity to describe this. Consider a surface with an area A acted on by a perpendicular force F. The pressure P that the surface experiences is defined as the perpendicular force F divided by its area A the force acts on. In SI units, the force is in Newton, the area is in square meter, and so the SI unit of the corresponding pressure P is Newton per meter squared. 1 Newton per meter squared is also called 1 Pascal. They are the same thing, and so Pascal is the SI unit of pressure. In calculation, Pascal is written as PA in short. So the pressure on a surface in SI unit is just how many Newton of force acting perpendicularly on per meter squared of the surface. This sort of tells how concentrated a force acts on a surface. Now, let's understand again the stabbing and punching example above, but with this expression of pressure. Even if we assume the same force during the punch and the stab, the much smaller surface area A on which the force is exerted during a stab, according to this expression, causes a much greater pressure P. So, a stab hurts more than a punch of the same force. As an example, consider a car of mass 2,800 kg at rest on the ground with its 4 tires, and suppose each tire has 100 cm square of area in contact with the ground. We want to find the pressure on the ground by each tire. As this is equal to the perpendicular force acting on the ground by the tire divided by the area of contact, we need to know this force acting on the ground by the tire first. To do so, we start with the free body diagram of the car. The forces acting on it are its downward weight and the upward normal reactions acting on the 4 tires. A quick refresher, the weight W of any object is related to its mass m through W equals mg, where g is the acceleration due to gravity and is equal to 9.81 meter per second squared on Earth. Now, by Newton's first law of motion, the 4 upward normal reactions are to be balanced by the downward weight. Assuming the 4 normal reactions are the same, we rewrite the left-hand side of the equation just as 4r, where r is the normal reaction on one tire by the ground. Another quick aside, whether or not these normal reactions on the 4 tires are equal depends on the position of the center of gravity of the car. This has to do with setting net moment being equal to 0. This is a big topic in mechanics. Anyway, solving this equation, R is equal to 6,867 Newton. But wait, to find the pressure on the ground, I need the force on the ground by the tire, but the R here is the force on a tire by the ground. Why am I even finding this R at all? Well, by Newton's third law of motion, the force acting on the ground by a tire and that on a tire by the ground are the same in magnitude, both 6,867 Newton. So now we can proceed to finding the required pressure by putting 6,867 Newton into this expression as the force. Just note that as this is the force by one tire, the area here is also that between the ground and one tire, which is 100 cm squared and converted to SI unit is equal to 0.01 meter squared. Finally, the pressure on the ground is evaluated to 6.87 times 10 to the power 5 Newton per meter squared, or more commonly 6.87 times 10 to the power 5 Pascal. However, in this chapter, we will just focus on the pressure in gases and liquids, collectively called fluids in physics. It turns out that anything immersed in a fluid experiences a pressure. Let's understand this from something I taught long ago. In liquids and gases, particles move around in random motion. For example, this animation shows how the particles in a gas move in a rectangular container. Obviously, the particles in random motion are constantly colliding on the container's surface. Considering that there are actually trillions of gas particles in a typical container, and the particles travel typically at hundreds of meters per second, even at room temperature, the collisions between the particles and the surface are extremely frequent, and so the force acting on the surface produced this way at any moment does not fluctuate too much. Such a force acting on the surface due to the randomly moving particles colliding on it, divided by the area of the surface, is the pressure experienced by the surface. That's why any surface immersed in a liquid or a gas experiences a pressure. And you know what? At this very moment you are listening to me, you are experiencing a huge gas pressure called the atmospheric pressure. The thing is, we as well as almost everything on Earth are surrounded by the air in the atmosphere. And so the air particles are constantly colliding on the surfaces of our bodies. This subjects us to the so-called atmospheric pressure, which is rather large. The standard atmospheric pressure, written commonly as 1 atm, is about 1.01 times 10 to the power 5 pascal or 101 kilopascal. There are various devices which can measure gas pressure. Bourdon gauge is one of them and is commonly found in a high school laboratory. Its main structure is a hollow curved metal tube connected to where the pressure is to be measured. This hollow tube works very much like a party horn. When the gas pressure inside the paper tube of a party horn increases, the paper tube uncoils, and when the pressure inside is reduced, it coils back. The hollow metal tube in a Bourdon gauge is almost the same. When the gas pressure inside it increases, the metal tube uncoils, but just a little bit because being a metal is much harder than paper to get uncoiled. As it uncoils a bit, the pointer attached to it turns around this dial to show the pressure. While the Bourdon gauge works, in some experiments you may want to record the pressure at regular and very precise time intervals, and you may also want a greater accuracy to detect small changes in pressure. Bourdon gauge is not useful in cases like this. Then you will need a pressure sensor. It's a small probe placed in the gas where its pressure is to be measured and is connected to a data logger. It gives quick responses and can record pressure at precise time. With a suitable software installed in a computer, it even allows plotting graphs related to pressure in no time. So that's the very basic of pressure. We'll start more detailed discussion about specifically gas pressure soon.